Good afternoon, everyone. My name is Xu, and the topic of my today's presentation is about the data-driven moment-curvature relationship modeling of corroded bridge columns using machine learning. The content will be divided into the following parts. I will start from our research motivation, and then I will talk about how we use machine learning method to assess solve problems. And last is the results and conclusions. The first is our motivation. As we know, in the risk assessment framework, fragility analysis is generally to be performed to assess structure failure probabilities and quantify the risk of structures under extreme hazards, such as earthquake. However, due to material aging problems and the degradation of structural capacity, failure probabilities of structures would get larger with the increase of service time. Among many reasons, reinforcement concurring is a principal cause of the deterioration of reinforced concrete structures. So for this study, we will mainly focus on the time-dependent seismic capacity of reinforced concrete bridge columns with consideration of corrosion. When corrosion of reinforcement develops significantly, it not only affects structure serviceability by cracking or even spoiling the covered concrete, but also impact on the structural safety by decreasing the load-bearing capacity of reinforced concrete members. Here we conducted a case study, and we consider the corrosion as a random process. So, and we can see that the corrosion initiation time is also a random variable, and the corrosion ratio of rebars and stirrup will increase along service time. And the material properties will also be affected by corrosion. When the corrosion ratio is given, the strength of steel and concrete materials could be evaluated by these equations. From the results of current case study, we can see that the strength of rebars and the concrete decrease along bridge lifetime due to corrosion. And besides, we noticed that the variance of the strength of rebars also increase when the service time increase. So for the column seismic capacity, we use moment curvature relationship of column section to describe it. Here, according to strength states of rebars, curved concrete, and core concrete, we define 4 limit states and 4 critical curvatures as capacity index. And accordingly, we could have different damage states of bridge columns. So now our purpose is to identify the 4 critical curvatures of bridge column sections along different service time with consideration of corrosion effects, so that we could establish time-dependent probabilistic capacity model, which is a cornerstone for fragility analysis. Next, we are moving into our methods. Instead of using traditional physical-based method to get moment curvature curves, we would like to leverage data-driven method to solve this problem. The main reason is that when dealing with a large number of sampling data, traditional physical-based methods have disadvantages on computational efficiency, while data-driven approach like machine learning is an efficient way in this case. Our method is to develop a multi-layer artificial neural network to map the relationship between input data and output data. The first step is to prepare the database. In the following slides, I will elaborate on how we set up the database. The second step is to optimize the neural network architecture. In other words, we need to identify a private 2 hyperparameters, that is, the number of hidden layers and the number of neurons in each hidden layer. And finally, we could evaluate the prediction accuracy of the in-based capacity model in terms of mean square error. The right image shows how we developed the artificial neural network model. Here, after dividing the database into training set and test set, we use 5-fold cross validation to optimize the architecture of the neural network. The training set was further divided into 5 subsets, and average performance of neural network is compared to identify optimal hyperparameters. Next is about data preparation. In order to set up capacity database, we selected certain structure-related and current environment-related parameters as input variables. And we use the Lane hypercube sampling technique to generate 500 samples as bridge column section database. And then we use OpenSys PY program to get moment curvature curves. The previous 4 defined critical section curvatures, phi1, phi2, and phi3, phi4 are taken here as output data for the neural network. And now we are moving to the results. The first part is the architecture optimization of neural network. These 3-dimensional figures showed the relationship of mean test error against the number of hidden layers, which is represented by the big N, and the number of neurons in each hidden layers, which is represented by big Q. In the first and for the first and second critical curvatures, phi1 and phi2, it can be observed that when the number of hidden layer is over 2, the mean error has an increasing trend. And when the number of neurons in each hidden layer is larger than about 20, the mean error would no longer decrease significantly. So for phi1 and phi2, we could identify optimal architecture of neural network when n is equal to 2 and q is equal to 20. For the third and the fourth critical curvatures, phi3 and phi4, it can be seen that the mean test error first decrease when q is smaller than 5, and then rise when q is getting larger. This phenomenon is a typical overfitting problem. That is, when a more sophisticated network is adopted, even though it can perform very well on training set, but at the same time, it will lose the ability of generalization, which means the performance on test set is getting worse. So here for phi3 and phi4, we could identify the optimal hyperparameters as n is 2 and q is 5. Okay, after we get the optimal neural network model, we could use the whole training data set to train the network and to see its prediction performance on test set, which is the new data for the whole network. So the result here shows a good agreement between observed data and also the between the observed data and the predict data. We can see that all the 4 critical section curvatures could be predicted in a good accuracy by the network. So here we can draw some conclusions. The first, reinforcement current could cause degradation of durability of reinforced concrete bridge columns by decreasing its bending capacity and curvature ductility. Second, The uncertainty from corroding process should be considered when develop time-dependent seismic capacity of reinforced concrete bridge columns. And third one is the neural network model with appropriate architecture is capable of predicting moment curvature relationships of reinforced concrete bridge column section with consideration of corrosion. Okay, I think that's all for my presentation. Thank you very much for listening.